Okay, so good morning, everybody, to my talk. Today I want to show you the power and simplicity of Flink SQL engine and also how it integrates in the entire ecosystem. Who am I? I'm Timo Walther. I'm committer and member of the project management committee of Apache Flink. I'm part of the Flink team since the very early days. I'm working as a software engineer at DataArtisans, and I'm mostly working right now on the SQL and table API. So who is DataArtisans, for those of you that don't know that? DataArtisans is the startup, the company founded by the original creators of Apache Flink. Their current offering is the DataArtisans platform, which bundles open source Apache Flink together with the DA application manager. Our goal is to provide very easy managing possibilities of having a streaming infrastructure, managing a zoo of stream processing applications. This is how our platform looks like. So as I said, Apache Flink in the core, the application manager that is tightly bundled, especially with Apache Flink's save point mechanism, so you can draw save points of your stateful application. You can use and transfer this save point to another cluster, spin up another testing cluster, do A/B testing with streaming application and so on. And it also is tightly integrated with logging metrics and other tools that you need usually in production. So if you want to try it out, there is a free trial available online. So for those of you who don't know about Apache Flink is a stateful stream processor ready for different tasks from streaming analytics to event-driven applications. It is used by many different companies, bigger and smaller ones. So one of the biggest contributors is Alibaba, but we also have Netflix, Uber. We have banks like the Dutch bank from the Netherlands, ING. And also Yelp, Lyft, and so on. So first of all, what is this talk about? Our talk is about SQL today, but there are also other APIs in Apache Flink. So if you really want to do a low-level, basic computation on Apache Flink, we provide the so-called process function. Process function gives you the main primitives of the framework, which is access to time, timer services, event time, processing time. It gives you access to state, so you can store data in state, and Flink is managing it for you. On top of that, we have the data stream API, which provides a bit more abstraction. So for example, with time and state, we provide ready-to-use windows, different windowing semantics. And on top of that, we built the SQL API and the table API for high-level analytical queries and so on. It is nice to mention that all those APIs nicely interact with each other. So you can, for example, use the table API and SQL for doing some ETL, and then once you get more complex things like event-driven applications, then you can also go back to data stream API with almost no overhead. So now let's talk a little bit about Flink's relational APIs. So first of all, we have ANSI SQL. This is not just a dialect of SQL. This is real standard SQL as it is common in databases. Additionally, we also provide a more LINQ-style API that you can use fluently in Java or Scala. This is especially useful if you want to integrate it into your existing data stream API application and you don't want to specify everything in just a stream. So here you have a more fluent way of programming a relational program. But the nice thing about both APIs, they are unified, so you can mix them also if you want. You can use SQL, but you can also use table API, and you can use the same query that you specified for both batch and stream processing data with the same results. And this is very, very important. So it doesn't matter if the input is static or streaming data, the result should be exact and the same. So how do we do that underneath? Both APIs come together. So first they are separate. Like we do some table API validation, and we do some SQL validation and parsing using Apache Calcite. But in the core, we are using Apache Calcite for logical planning. Of course, you can also ingest your custom external catalog and other data sources. We are using Calcite for optimization and included custom rules that are then compiled down either into Flink's dataset API for batch processing or into a data stream API for stream processing. So let's quickly look at a simple example. Let's just assume we have a clicks file consisting of clicks of a user, and we just want to count the clicks per user. I mean, if we are in a batch world, this is fairly easy. We just scan this table, we compute the count, and then at the end, we just produce the result once, and that's it. That's how the batch world works, right? How does it work with streams? So what if clicks is just a stream? The problem here is the events are coming in, so they are not available at once, so they are coming in from time to time. And this means we need to be more flexible about the output, which means in this case, Mary has just a count of 1, but then there are more rows are coming in. And then if there is the second event, we have to actually update our result and update our result at the end. But as you can see, in the end, the result is exactly the same as in batch processing, and this is our goal, even though this table is continuously updated. So why is actually this unification of batch and stream so important for us? So first of all, we wanted to improve the usability. And as I said, we don't want to have a custom SQL syntax. Who knows, maybe in 10 or 20 years, Flink is not the most important processor anymore. So what are you doing with a bunch of jobs that you have written? And SQL is the way to go because, I mean, it hasn't changed for the last 40 years. And it's very likely that it won't change in the next decade. That's the first thing. And the nice thing about SQL is actually you're not specifying the runtime. You're just expressing what you want. It's a declarative language. And the semantics are pretty clear. And actually every computer scientist should know about that. Another thing is portability. Because the nice thing is when you write a SQL, you can run it on bounded and on unbounded data with the same runtime, basically. So for bounded queries, for example, you would always look at a certain window of your stream, but actually your data is produced as a stream, right? The nice thing about a stream processing application is you can decide when you want to start the processing, so at which time in your stream you want to start. But then you can also compute the future, basically. So it's a continuously running query instead of just having a discretized stream all the time. So the question is, how can we do the same SQL semantics on streams? Actually, this is not a very new topic. It was already there, and there's also a lot of research already out there in papers. Because running queries on streams has already been researched in the area of materialized views and materialized view maintenance. Because in this area, usually it was we needed materialized views to speed up our analytical queries. Usually, we had no access to the base table, so we were consuming a database log, for example, so like insert, update, and delete statements. And the materialized view was just evaluating this stream and also updating a result internally, right? So we are using a similar technique in Apache Flink. We call this concept a dynamic table. So a dynamic table is not fixed. It is changing over time. You can convert a stream into a dynamic table. Then you can query this dynamic table, and the result is again a dynamic table that you can either use for the next query, or you can convert it back into a stream or write it into a file, whatever you want. The important thing is dynamic tables are just a concept. That doesn't mean that you have to hold the entire streaming data that is coming in state. No, you can just see it as a concept, and Flink is only storing internally as state what is really necessary to execute this query. For example, if we are counting, then we would just count we would just keep the current count per key in the state, for example, not the entire rows. How do we convert between streams and dynamic tables? So we have 3 different conversions that a user can perform. So first, the first conversion is append conversions. This is when you have a stream that is just inserting things, so that you don't have delete messages. It is a continuous stream of inserts. Then you can also have upsert conversions, which means records come with a already unique key. It can also be a composite key, of course. And then you want to update results. So I don't know, there is an event for a particular user ID, and then you just want to update, for example, a join result that was computed out of this key. Another thing is changelog conversions. So maybe you don't have a key, but you just want to delete an entire row or an entire, or you would want to update an entire row. You can also do this very easily. So what is the feature set in Apache Flink right now in 1.5? So first of all, of course, the very simple use case is just having a select from where query where you can perform some projections and filtering. The next step would be like maybe having some aggregates. So we support regular group by queries, so non-windowed aggregations on streams. But you can also do a windowed aggregation. So we provide three different types of windows: tumble windows, hop windows, or also called sliding windows, and session windows. I will show you an example later. We also support joins. So first of all, we support non-windowed inner joins, so as you know them from regular SQL. And we also support time-bounded joins, because the problem with inner joins is that the state can, in theory, grow very heavily, especially if you have a lot of data coming in. So usually what you want to do is you want to bound, or you want to join 2 streams on a common time frame, basically. We also support a lot of extensibility, so you can define your own scalar functions, aggregation functions, tabled value functions. And I will also show you a demo today, because we are also working on the ecosystem to improve the ecosystem around the SQL engine. Since this version, we also offer a SQL CLI client, but this is in a very early stage right now. The nice thing is everything on the top is supported for batch and stream processing. So just you can run it on both in both ways. For streaming in particular, we also offer things like over windows, SQL over windows with unbounded and bounded preceding semantics, and things that are actually only applicable to batch, like a union, intersect, accept, and an order by, so a global ordering of your entire data. This is supported for the batch part, but might also be introduced in streaming soon. So what does it mean? What can I build with this actually? So first of all, data pipelines. You can transform, you can aggregate, you can move events from one system to another system in real time. You can have low latency ATL, so no need for doing this as a batch job. You can also use streams for that. You can connect to your favorite file system, database system, key value stores, because the nice thing is, as I said, the result of this continuous query is a dynamic table, which means it is a stream, a changelog stream of events, and you can decide what you want to do with this changelog stream. So you could either just dump it into a file. You can update the actual materialized result somewhere in a key value store. You can update it in a database. You're very flexible about that. And yeah, the stream and batch analytics, so on both types of data. You can also, like for example, you could store it in a key value store, and then you connect this key value store with your favorite visualization framework, and then you have, for example, a live dashboard. So let's look at some examples. For the examples, we have a publicly available data set. Maybe you know that. It's a New York taxi rides, the New York taxi rides data set. It contains taxi ride events. So you get an event with a position for every pickup and drop-off of taxis in New York City. So every event has geolocations and also a timestamp involved. So let's look at how could we use SQL. For example, if we just want to identify the very popular pickup and drop-off locations in New York City. So in this SQL query, what we are basically doing is we are specifying a window, a hopping window of 15 minutes length every 5 minutes, and then we look into this 15 minutes. We look into this 15 minutes and just count the number of departing and arriving taxis during this time. Yeah, and to mention that in the subquery in the middle, we are just assigning a cell ID. So we're basically building a grid out of New York City. We're assigning the geo coordinates to some cell, and then we count within this cell and also output that. Another example is, how could we determine the average ride duration for a pickup location? For this, we need to join actually two streams. We need the stream of start events, and we need the stream of ride events. We join them on the ride ID, and then we can compute the average ride duration. And in this example, we are using these windowed joins. So as you can see here in this part, we have an additional predicate that says, okay, from the end events, we take the timestamp, and this timestamp must be between, and then you can see the timestamp of the other stream or the other table, because we are in SQL, other table. So it must be between this or interval of 1 hour. So it's a window join of 1 hour. And as I said, it's SQL. So usually, I mean, you have to get used to the syntax again, maybe, but it is standard SQL. So everybody should get this. And actually, it doesn't need much more. So you can use the SQL, run it on Flink. You can connect it with some pub subsystem like Apache Kafka. Then you dump it into Elasticsearch, connect it with Kibana, and then you're actually done. And then you have your streaming application ready to be used. So that sounds great, right? But the problem right now is, how can we use it if people are not that familiar with Java and Scala? So in the Flink community, we get this request all the time that especially data scientists and less skilled people need a way of defining such streaming queries, but they don't want to integrate the SQL into data stream or data set APIs. What they really want is an easier way of shipping this SQL query, not as part of a Java application, and not having to deal with Maven or other build tools and so on. So in the past years, past 2 years, I would say, the community mostly focused on internals. So at the core, at the engine, which means we added a lot of operators, types. We support POJOs, and yeah, every Java object can be used within this SQL API. We worked on the extensibility. We support different UDFs and external catalogs and so on. And this core has already been proven because it is used at Alibaba in their cloud offering. It is used in their public cloud offering of Huawei, of Uber internally. But all those companies built basically their own submission system and their own connectors library. What we are working on right now is we have to improve the usability because we have a good core, but maybe this core is not that accessible right now. So what we are trying to do now is we want to have a CLI, we want to have better catalog integration, more table sources, more table syncs. That's on our agenda for the next releases. But as I said, we have already one very early development going on, and I want to show you how this looks like. So I will give you a short demonstration of our SQL client. So first of all, I already have a running Flink cluster on my machine. It's just one task manager with 4 task slots. I also have a prepared Kafka, so I have a Kafka topic with some JSON data inside. So this is the regular Flink distribution. Beginning from 1.5, you have an additional binary file in the distribution called where is it here? SQL client. The SQL client can be configured using regular YAML file. So we can also look into this YAML file here. So this is how you configure the SQL client right now. But we're also working on having maybe like something like a DDL, so SQL DDL interface soon, where you can also specify tables and so on using a DDL statement. For now, we have this YAML file. So here you can define your table sources. You define the resulting schema as you would do it in a SQL DDL statement. You give some additional metadata, how you want to handle timestamps, because we also support streaming concepts like event time, so also dealing with late events and so on, out of orderness. So you can specify the metadata about timestamp and how you would emit watermarks for this timestamp. Then you just define your connector and some properties for this connector. For example, we have Kafka here in version 0.11. You define some format. In this case, it's JSON. You can use this type of string to define a schema, but you can also use a regular standard JSON schema. Then you can also enter some execution properties like a result mode. I will come to that in a second. Parallelism, and so on. So let's just run the SQL client. So this is the SQL client. You can get some help, so there are different things supported right now. So for now, the SQL client is just for prototyping, for playing around with Flink SQL. So let's just run our first streaming application, a very, very easy and senseless streaming application, but it works. You can just do a select 1+1 and let the stream processor compute this result for you. So in this case, as you can see, maybe I can make it a little bit bigger. Just a second. Yeah, as you can see, a stream processor can also count 1+1. In the background, we already submitted this job to the cluster, so it is already done. As you can see here, we submitted this job. You can also do a little bit more complex things, like here, for example, we just create a data stream by providing some values. We count on this data stream, we group by name, we submit this to the cluster. Also works fine. And you can also now let Kafka be involved here. So we have one table right now. Let's just print out our Kafka topic. Yeah, and here you can see the data is coming in. You can also stop the retrieval for a second. You can explore the data. You can open a row if you want. This is how our row looks like right now. So very nice for developing SQL queries. So let's go back. So right now it is just a very nice toy, but the problem is, can we use it for anything serious? And the answer is right now, no. It helps in developing a SQL query, but then you have to insert this SQL query into a Java application. What we are planning is what we call a SQL query service. This is you can get more information for that under FLIP 24, so Flink Improvement Proposal 24. Our goal is actually also tightly integrated with table catalogs and so on, where you can then also integrate it with tools like Apache Zeppelin and dashboards. There's, however, one challenge that we have to address here. We have unbounded input data, and unbounded input data also means we have unbounded results. And how do we deal with unbounded results? I mean, for the left query, this is just an append only without insert and deletes. This is very easy. The result rows won't change, so we can consume them. We can also buffer them if we want to, but then we can also drop them very easily. But how do we deal with continuously updating tables, right? So that means this result table must be maintained somewhere to access it. So either we consume the changelog, or we have to update a materialized table somewhere. And this is where this SQL query service comes into play. So this is just a design. It's not implemented yet, but it will be, in parts, it will be part of the next Flink release. Our idea is having like a REST API where an application can connect to this query service, submit the SQL query. The query service has access to all external catalogs in the cluster, optimizes the job, submits the query to Flink. Flink then runs this job and outputs the results to an event log or database. And since the query service knows the query, it also knows how this result has been written out by Flink into, for example, the database. So it can provide a way to serve the results back to the application. This means the application can only use REST, but you can use you can then use the connectors that the query service provides for running your distributed application. However, there is one drawback. In this case, the application does not need a special client because we are just communicating with REST. And most of the logic happens in the cluster, so the query service would sit in the cluster, and you just have to open one port for the REST communication, basically. The problem, however, is then the query service actually becomes a bottleneck. Because, I mean, you have your fault-tolerant Flink application here, but what happens if the query service goes down? Then all your applications that are consuming from this REST interface would have a problem, right? So our idea is actually also to provide something like a servicing library that just gets back a result handle from the query service, and then the servicing library communicates with the involved system automatically. So it would, for example, communicate or abstract the communication to Kafka or to a database or HDFS. That would solve the need for the query service, so it could go down, and the application and the streaming application are not affected by that. So this is a very, very early design. It's not final yet. So it would be very helpful if we get more feedback how we should design such a system. Check out FLIP 24 or the corresponding Jira issue, or just share your ideas online, and we're either on Jira or on the dev mailing list of Apache Flink. So just to give you a rough summary, we have identified unification of batch and streaming as a very important goal. It already solves, so we already solve a lot of those tasks. Flink SQL runs in production at Alibaba, Uber, and others, and the community is working on improving the user interfaces, and we are always looking for getting more feedback. If you want to learn more about Apache Flink in general, there is also a Apache Flink conference in September in Berlin this year, where we also offer training, a training day with advanced trainings and basic trainings. So if you are interested in that, now you get early bird prices. Might be worth looking into that. Otherwise, there is also a book coming up this year. This is written by one of the committers of Flink, so it will be a very, very good book. Some of the chapters are already available online, so might be worth looking into that if you're new to Flink. I think the introduction chapters at the beginning are already very helpful if you want to get started with Flink. Yeah, and we are also hiring, and if you're interested, you can also follow either me, Data Artisans, or Apache Flink to get more information. Thank you. Are there any questions? Yes?
Flink in relation to Apache Beam?
That's a very good question. So first of all, I think we are in a more like a friendship. So Apache Beam, I mean, the goal of Apache Beam is having a common denominator over all stream and batch processing frameworks, right? Actually, a lot of committers are from the Flink community as well. So I think Flink is the best supported open source runner on Apache Beam right now. We're also relying on things like better. So for example, we have a Python API. But actually, I mean, Python on a JVM-based language is a bit tricky. That's why we're also relying on Apache Beam. Maybe they can speed it up. The problem, however, is it's just a common denominator. So if there is a new feature in Flink, yeah, it might take some time to get it into Beam, or maybe it will never ever be integrated in Beam because the other runners don't need it, and they won't integrate something that is just particularly useful for Flink. So you always have to think about that if you want to use Apache Beam. And one other thing is, usually, I mean, you don't change your runtime all the time, right? So, I mean, Apache Beam tries to make the runtime exchangeable, but usually you don't do that very often because you have to run your tests anyway against the actual runtime. So, yeah. Yes?
One use case like end-to-end, maybe identity for all. So you showed the Flink SQL and franca. How is it embedded in a streaming flow? Like it's its own streaming application on Kafka, giving the Uber aggregates or something, or it's embedded into Spark, or it's
No, it's running on Flink. So everything is, so when you submit a query, this query is translated into a Flink job, and Flink is its own engine, yes. A true streaming-based engine, yes. Other questions? That's a very good question. I would say, I mean, the problem with Kafka Streams is that it is bound to Kafka, right? So this is one of the major things, because there are other stream storages coming up, like Apache Pulsar, Pravega from Dell, EMC is coming up. So, I mean, Kafka Streams is just bound to Kafka, and they can do some very nice optimizations. But if you want to be future-proven and want to support different types of streaming connectors and so on, and having more like not just only consuming from a topic and then writing to a topic, but more like a event-based, more complex application, then Flink is the way to go, I would say. Other questions?
how is it compared to NiFi?
I don't know much about NiFi, to be honest. I don't know. Other questions? Okay, then thank you very much.